Hello everyone and welcome to this unusual class. I regret very much not being able to be in class for today, but thank goodness for technology. At least you can see what I was going to do even without my being there. So we're continuing with seeing how to use L'Hopital's rule, and in particular today we're going to focus on how to apply L'Hopital's rule in situations where the indeterminate form is of the type that has the variable both in the base and in the exponent, like in this situation. So we start as in the usual procedure. That is, we're going to check what form this is. And of course, once we look at this particular expression, we notice that the portion inside brackets, as x becomes huge, becomes 1 plus a very tiny quantity which goes to 0. So the base of this power approaches 1, and of course the exponent approaches infinity. And therefore we have a form of the type 1 to the power infinity, which, as I explained in the pre-class lecture, is an indeterminate form. However, this is not a form to which we can apply L'Hopital's rule, so we had to do something to change it to a form that we can work with. And the usual trick is that of applying logarithms. I'm going to apply logarithms for this first example in a way which is a bit different from what I showed you in the pre-class lecture. Namely, what I'm going to do is I'm going to compute the limit as x approaches infinity of the logarithm of the whole function. And of course the reason is always the same, because this allows me to bring the x down away from the exponent position as a factor instead. And if we check again the form, at this point we notice that the x goes to infinity, and now because the 1 plus a over x goes to 1, the logarithm of 1 plus a over x goes to 0, and so we have a form of the type infinity times 0. Still not of the right type. Well, all we have to do is we modify it algebraically as we have seen last time, move the x to the denominator, and now we have something of the form 0 over 0. So now we're ready to switch to derivatives. By the way, I forgot to write down 0 over 0, but you can see that the numerator goes to 0 as we knew before. The denominator is x to the negative 1 with x going to infinity, so x to the negative 1 is just 1 over x, so that goes to 0 as well. So now we can use L'Hopital's rule. We switch to derivatives. The derivative at the top using the chain rule is going to be the reciprocal of the inside of the logarithm, which turns out to be x over x plus a. If you're not convinced, pause the video and check it on your own, times the derivative of the inside, which is going to be minus a x to the minus 2. Again, you may want to check that on your own. The derivative at the bottom is more immediate, it's just minus x to the minus 2, and now we have an x to the minus 2 both in the top and in the bottom. We can cancel them and we can combine what's left in the top, and so we're just left with the limit as x approaches infinity of ax divided by x plus a. By the way, a can be any number. I forgot to say that at the beginning, but a can be any real number except 0, of course. But for x equals 0, it's not even an indeterminate form, so we're fine. Now, the limit, this last limit now is very simple, and we can use either L'Hopital's rule if we want to, or simply the law of the jungle, or whichever method you want. And it turns out that the limit is going to be equal to a. But remember, this was the limit of the logarithm of the original function. So in order to get the original limit, we have to raise e to, we have to undo the logarithm, which means raise e to whatever power we have found. So that means that the limit of our original function is equal to e to the power of this number a that we have obtained. And so that is the limit of the original limit. Now, what happens when a is equal to 1? Well, of course, when a is equal to 1, we end up with the limit as x approaches infinity of 1 plus 1 over x all to the power x. And its limit turns out to be just e. So first of all, this is a very clear demonstration that 1 to the power infinity is in fact an indeterminate form, because it will change according to what a is in this case, but also tells us how to get e as a limit, namely as the limit as x goes to infinity of 1 plus 1 over x all to the power x. Alright, you're probably going to be able to see this limit or some variations of it as you go through the examples and exercises. Now, Oh, by the way, always check some graphs. Of course, because we have an a which is indeterminate here, you may want to check more than one. So graph the function 1 plus 1 over x all to the power x, and then graph the function 1 plus 2 over x all to the power x, and so on, and check that in each case the limit is going to be e to the power of the corresponding a. Now, let's look at another example which is similar to that. Again, we have something of the form a function of x raised to a power which also includes the variable x. And this time I'm going to use the same technique that I showed you in the pre-class lecture. Namely, first of all, we're going to check what form it is. And of course, as x goes to infinity, the base goes to infinity, and the exponent goes to 0, since it's 1 over a huge number. And as we saw in the pre-class lecture, infinity to the power 0 is an indeterminate form. Again, not of the type that we can use with L'Hopital's rule. So we're going to change it. The way we're changing it, we're going to write the base as e to the power ln of 1 plus 2 to the x. Remember, every positive number, and certainly 1 plus 2x is going to be positive as we go to infinity, can be written as e to the power of ln of the number itself. At this point, I have a power of a power, and I can combine the two exponents into a single one by simply multiplying them. So I end up figuring out that what I'm computing is the limit as x goes to infinity of e to the power ln of 1 plus 2x over 2 ln x. Now, if you look at what happens to the exponent, which is now the only place where x appears, this turns out to be infinity over infinity, which is exactly what we need for L'Hopital's rule. So we're going to apply L'Hopital's rule this time to the exponent only. Remember, we can do that because with the limits the anti-Murphy law works, and so e does not create any problem. So the only problem with the limit is in the exponent, so we're going to focus on that one. So as we compute the limit as x goes to infinity, all we have to do is take the derivative of the top and the bottom, and I'm going to therefore write it in this way. Now notice that I'm missing something, haven't I? In my hurry to prepare this class, I forgot to put the little h on top of the equal. Remember, according to L'Hopital's rule, I cannot say that the first limit is equal to the second until I've found that the second limit exists. And therefore at this point I can't really say that they are equal. But again, we're using L'Hopital's rule, so provided that the second limit exists, that equality does exist. Is valid, I mean. So I guess you can check on your own that those two derivatives are correct. Now what I can do is I can cancel the 2's from the top and the bottom and do a little bit of algebra. And again, if you're not quite sure about it, you want to pause it and do it on your own. And now we end up with a fairly simple form. Now again, this is an indeterminate form, infinity over infinity, but we can use the law of the jungle or divided by the highest power, or if you want to use L'Hopital's rule again, and we're going to find out that that limit is equal to 1/2. So notice that at this point again we're not finished, because we computed only the limit of the exponent. We still have to put that exponent in its place, which we're going to do now. So the conclusion is that the limit of the function we're looking at is e to the 1/2 or root e. So again, this is another situation where these limits end up being some power of e in some form or other, which is not surprising because of course we're using exponents and we're applying natural logarithms and so on, so somehow e pops up somewhere. Back to some very simple examples here. Some students had asked me in class, can we apply this rule with hyperbolic functions? Well, of course we can. You can apply to any function as long as the assumptions are satisfied. So in something like this, remember that both sine and hyperbolic sine both go to 0 as x approaches 0. So if we try to compute this limit, it turns out to be something of the form 0 over 0, indeterminate once again. And so, but it's indeterminate of the right form, so we can switch to the ratio of derivatives and apply L'Hopital's rule. Well, the derivative of sine is cosine. Of course, applying the chain rule, we also have this additional factor of 2 in the front, coming from the 2x inside the sine, and the derivative of sinh is simply cosh. Well, now cosine and cosh both go to 1 as x goes to 0, so that limit turns out to be 2, and that's it. So as you can tell, very easy situation. This is really not an issue at all. Now, speaking of the assumptions, remember that the assumptions, as I said, can need to be checked, and quite often we don't do it because in pretty much all of the questions that we're going to be dealing with, those assumptions are satisfied. But still, you want to be careful about those assumptions. I'm going to show you a little example where the assumptions don't work, just to demonstrate it. In fact, they are needed. They're not there just to give you a hard time. So let's look at this particular function and this particular limit. Limit as x goes to infinity of x minus sine x squared divided by x plus sine x squared. If I actually check the form, that's infinity over infinity, but we can apply actually the law of the jungle and notice that both the top and the bottom, the sine term really in the long run does not add much, because as x goes to infinity, the first term, the x on top and the bottom, becomes huge. Sine is only between plus and minus 1, and it's not really going to do anything to it. So for large values of x, this fraction simply becomes just x over x, which is just 1. So we can see that quite easily. But what we can do is we can say, well, it's infinity over infinity, we should be able to apply L'Hopital's rule. Well, let's try and apply it and see what happens. So we're going to switch to the derivatives. So the derivative on the top is going to be 1 minus 2x cosine of x squared divided by bottom, same thing, but with a plus. And I'm just using the chain rule there. Now, if I let x go to infinity, what happens now? This time, the 1 becomes the part which is going to be irrelevant, because x is going to become a really big number. And therefore, the 1 can be eliminated, and this thing ends up being, or if you want, even more formally, I can divide top and bottom by x, and so I end up with this particular form. Now the 1 over x goes to 0 both in the top and the bottom, and so we can cancel that, and after we cancel that, we end up with two parts, the numerator and the denominator, both having cosine of x squared and a 2, so we can cancel those. All we're left are the plus on the bottom and the minus on the top, which end up giving us a -1. But now notice, the original calculation based on the law of the jungle gave us a value of 1. The new one gives us a value of -1. Why the discrepancy? So you can see that in this situation, L'Hopital's rule doesn't work. Well, here we have to check the requirements. Remember, what are the requirements? First of all, we need something of the form infinity over infinity or 0 over 0. Well, we have that. The other assumption is that both the top and the bottom must be differentiable functions. We have that too, of course. Both the top and the bottom are easily differentiable. But there is another assumption that we often forget to check. And the other assumption, remember, it has to do with the derivative of the denominator. And the assumption is that that derivative cannot be equal to 0 in a whole interval around the value we're approaching, except possibly at that value. But let's graph that function. The graph of that function looks like that. And now you can see that that graph, in fact, that function ends up becoming 0 infinitely many times when you get close to infinity. So it doesn't matter what interval around infinity we use, our denominator, or the derivative of the denominator, becomes 0 infinitely many times, and that's contrary to the assumptions, and that's the reason why in this situation L'Hopital's rule doesn't work. Now again, this is just a curiosity for you. Don't worry about this showing up in a test or a quiz. It will not. I just wanted to show you why that requirement is there, and again, it's not just a little quirk, but it's something that is quite needed. Let me show you instead now another situation that can occur, and that has to do with a different kind of indeterminate form. Now if you check this form in this particular situation, remember ln of 1 is equal to 0, so that means that in this situation the first fraction becomes of the type 3 over 0, which goes to infinity. The other fraction also of course goes to 2 over 0, which is also infinity, so we end up with something of the form infinity minus infinity. Again, this is an indeterminate form, not of L'Hopital's rule type. So we need to change our formula algebraically. So we're going to do that by using a common denominator. It's a difference of two fractions. So when we do that, we end up with this expression. Again, you may want to pause and check on your own that that is in fact the right expression. And now we can, if we check this one, we end up with noticing that this is a 0 over 0 kind of form, because again, as x goes to 1, in the numerator we have a 3 minus 3, which is 0. The logarithm of 1 is 0, so everything becomes 0 on the top, and similarly in the bottom. So now we are in the setting for L'Hopital's rule, and we can compute derivatives in the numerator and denominator. So as we do that, this is what we end up with. Again, you may want to pause and check the calculations on your own. Once again, we're going to do a little bit of algebra, get rid of that common x in the denominator. Once again, pause and check on your own. And now we're done. Well, almost. Let's see what happens when x approaches 1. Well, in the numerator we have 3 minus 2, which we can easily check to be 1. In the denominator we end up with a ln of 1, which is 0, and a 1 minus 1, which is also 0. So we end up with a 1 over 0. And as you by now I hope know, this gives us an infinity form, but we're still not sure whether it's positive infinity or negative infinity. So you may want to check it on your own, both algebraically and through the graph on your calculator, to see that in fact this limit ends up being positive infinity from the right hand side. Remember, the key point here, if you're going to check it algebraically, I'll leave that to you, is to notice that we're approaching 1 from the right hand side, not the left hand side. So here is another resolved situation. Again, notice that the conclusion of L'Hopital's rule applies even when the limit is in fact infinite. One last example, which I'm only going to work out very partially, and I'm going to let you work out the rest of the details as an exercise. And again, this particular video is going to be a little bit shorter than the corresponding class, because I don't have your questions and I'm missing them. But I hope you will have lots of questions to ask me when I come back. So let's look at this last example. We start as usual by checking the form. Oh, and by the way, here I'm assuming that both n and m are positive integer numbers. The situation becomes a little bit more complicated if you have numbers which are not integers, and we have to be a little bit more careful. We'll leave that alone. So let's see. In that situation, then both the top and the bottom go to infinity, because of course the logarithm becomes huge. We raise it to some positive power, it becomes even bigger. The denominator is big by itself, and we raise it to a bigger power. So again, both top and bottom become infinite. So we can use L'Hopital's rule. So we switch to the ratio of derivatives, and let's see what happens. On the top we have to use the chain rule, in the bottom just the power rule, and this is what you end up with. Again, pause and check on your own. Now we can do a little bit of algebra on this one, and what this entails is pretty much just moving that 1 over x, or changing that 1 over x in the numerator, this fraction here, setting it to the side, and then combining it with the x which we already have in the denominator. And notice that now what we have is pretty much the same expression we had at the beginning, except that now we have an n over m in front. Well, that's just a coefficient, and the power of ln x has decreased from n to n minus 1. Well, now what I can do is you can check this again. Assuming that n was not equal to 1 to begin with, then this thing is again a form just like the original one. It's going to be infinity over infinity, and we can keep applying L'Hopital's rule. But notice, each time we do that, the exponent gets of the numerator gets decreased by 1. And therefore, if we do this enough times, well, what is it going to happen? I'll leave that up to you to finish it and think about what's going to happen. It's really not a big deal. I'm sure you'll be able to do it on your own. If not, you can ask me when I come back. But here is another thing for you to think about. What this limit proves is that for large values of x, any power of the ln x eventually grows slower than any power of x, even if the power of ln x is going to be much bigger than the power of the x in the bottom, the top eventually will end up growing slower than the bottom. Now, if that confuses you, you may want to listen to that again and think about what I'm saying after, of course, you have arrived at the conclusion of what that limit is. But I'm going to leave that to you to think about and consider. So that's it for the rest of this class. It was not much, as you can tell. Keep watching it and make sure that you understand all the details of it, and then talk to me for anything else that remains unclear when I come back, which hopefully will be soon.